Let's start. Good afternoon, everyone. Welcome to the NITheCS Mini-school on the From Physics to Machine Learning and Back. And today is our last lecture, and the lecture will be given by the Cameron Beetar, who is the PhD student at UCT with Professor Murugan, and he will tell us about the machine learning of many-body localization, a practical introduction. Okay, Cameron, it's your show. Please take it over.
Okay, let me check. Can you see that?
Yes, perfect.
Okay.
Yeah.
Hello everyone, and thank you for the invitation, Prof Shock, and the introduction, Ilya. So what I'm going to try and do today is sort of roughly introduce ideas from many-body localization and machine learning, in particular artificial neural networks. One of the difficult things when composing a talk on this is that you'll have people who are experts in many-body localization and people who are experts in artificial neural networks. And so you'll feel comfortable in one section and uncomfortable in another. And there are lots of details that have to be swept under the rug in order to make this sort of fit within a 1-hour lecture. But yeah, let's get cracking. So the big picture is we have this physics problem, and the physics problem comes with a sort of set of inputs, and that will come in the form of your Hamiltonian and the free parameters of your Hamiltonian. The thing we want to avoid insofar as is possible is this hard computation numerics. We want to be able to generate results without having to do complicated, difficult, high-performance computing numerics every time. And the outcome we want from this particular problem is whether or not the system thermalizes or localizes. And sort of the map between the two problems comes in the form of an input. So your problem constituents are mapped to an input vector. The hard computation numerics are replaced by your neural network. And the outcome is some probability. In this case, it'll be a probability of being localizing or thermalizing. Okay, so onto the introduction of localization. Right, so we're going to take a developmental perspective, and what that means is we're going to start right at the beginning with your quantum mechanics. So quantum mechanics is your essentially isolated quantum systems, a small number of quantum degrees of freedom that interact via some potentials. And I included the hydrogen wave function here because sort of every undergrad in physics has had to solve for the wave function at some point. Okay, but now we want to move on to something a little bit more complicated. We want to understand how experimentally we can sort of do things with these quantum systems. And in experiments, you typically have very good control over things like pressure, temperature, volume. So these big macroscopic variables. And we want to know if I don't have fantastic control of the microscopic details, but good control of the macroscopic details, how do I model this? And so we get our answer from classical physics in the form of statistical mechanics. So that takes us to quantum statistical mechanics. So here we have the quantum system. So this is like your initial pure quantum mechanics placed in contact with a reservoir. And that reservoir is going to have your macroscopic properties like pressure, volume, temperature. So this is sort of a classical type of object. And what we make use of is, in terms of having poor control over the microscopic degrees of freedom, is this idea called ensembles. So we say I don't have, or you might say I have no control over the initial state or some control over the state of the quantum system. And so you essentially average over those expected initial states of the quantum system to get an expected behavior of the system overall. But in going from quantum mechanics to quantum statistical mechanics, it feels like we've made this big jump. So we've gone from a small number of quantum particles to a small number of quantum particles in a big sort of classical object. What happens when I separate the quantum particles from the classical object? Will it still thermalize? So that's the thing that we typically see where a quantum system equilibrates. And so we want to know, if I make that quantum system big, what is that? and what happens? Do I still see thermalization? And that takes us to many-body quantum mechanics. So here you have a purely quantum system and a large number of quantum degrees of freedom. So a large number of quantum particles interacting by whatever potential you've chosen, or interaction term you've chosen. But in this case, so we have this battle between unitarity and thermalization. So unitarity is coming from our initial quantum mechanics, so our small isolated quantum systems. And here we know that you can time evolve the system forward, and once you've got an end state, you can also reverse the time evolution to recover your initial conditions. With thermalization, so that's your quantum system reservoir, you have, well, with thermalization, you basically have that almost all of these initial states, or all of the initial states tend towards a thermal state. And so no matter where you start, you end up the same place. And that means that I can't time reverse and recover my initial conditions. So I've lost information about the initial state of the system. Right. So this brings us to the sort of a key question of this talk is, if I have a large purely quantum system, is there a way for that system to act as a reservoir for a subset of that system? Okay, so let's try and motivate why many-body quantum mechanics is interesting. So we're getting good at small experiments, and my key example of that is Professor Blumenthal building his dilution fridge, which is at UCT. And here we have very good control over individual particles. So this is single electron control, but our small experiments are getting a little bit bigger. And the key example of that is actually given to us by quantum computing. So here we want a large number of quantum degrees of freedom in order to perform complex computations. And so the state of the art at the moment is the IBM's Osprey, which is 433 qubits. So those are interacting quantum particles, but they have plans to make them bigger. So our initial idea of sort of quantum mechanics being a small number of quantum degrees of freedom is growing into something which is starting to look sort of more like quantum mechanics meets a reservoir type thing if I were to partition the system. And as a final motivation for the theorists listening, I just included it. It's OTOCs, or out-of-time ordered correlators. So they're an idea that initially came from superconductivity, but are currently being used to probe the scrambling properties of black holes. But there's a whole bunch that can be said about this, which it's just not quite relevant. But OTOCs are also used in understanding quantum phase transitions. So I've added some references at the bottom here, but I'm not going to speak about this at all further. Okay, so we've spoken about localization and thermalization, and now I wanted to give you the context of where we're going to actually apply these ideas. And so what we're going to be interested in is this thing called the nearest neighbor Heisenberg spin half chain in the presence of a disordered field. Okay, so let's break that down. The nearest neighbor bit basically just means that for each vertex, they only see a partner on either side of them. They don't see any others. So for instance, this guy at the top doesn't see the guy at the bottom. The spin half bit just means that at each site, I have a 2 eigenvalue system. So it's a plus minus, an up down, a 0, 1, however you want to represent it, but it's only got 2 eigenvalues. And the disordered field bit is something that's a little bit tricky to explain with this diagram, but it'll become more apparent later. What that is basically saying that at each site, there's a parameter which is local to that site, which is controlling the strength of the Hamiltonian at that site. Okay. And what we're going to do is we're going to extend our interest from this sort of ring structure to structures that have quite different topologies. So we're going to train our neural network on data that only comes from these rings. And we're going to ask it questions about these other systems. So the system that looks a bit like a wheel, the system that looks a bit like a star, and this system, which is almost the same as the initial system, except here I've got not just nearest neighbor connections, but next to nearest neighbor connections. Right. Okay, so those are the systems we are going to be interested in, but what is it about these systems that we're going to try and study? And what we're going to study, well, what we're going to be interested in is this battle between unitarity and thermalization. So sort of a quantum mechanics idea and a sort of statistical physics idea. So, and we're going to ask who wins the battle for these systems. But then the question becomes, what are the criteria for deciding who wins between unitarity and thermalization? Okay, so representing the thermalization side, we have this thing called the eigenstate thermalization hypothesis. I'm not going to try and state it verbatim, but roughly it says that in the thermodynamic limit, local observables, so that means that if we're looking at a system like this, I can look at a subset of the system. Local observables of the many-body eigenstates should take on values associated to the observables being in a thermal ensemble. So that basically means that in contact with a reservoir. And so that statement can roughly be summed up as the whole system can act as a reservoir for its subsystems. Right. So that's who's representing thermalization. Now for unitarity. So on the unitarity side, we have this idea called many-body localization. And in these systems, you have at least partial information preserved about the initial conditions. And it's quite hard to explain it sort of without looking at the Hamiltonian. So here's the Hamiltonian for the ring structure shown. This HI is that local parameter, the local disorder parameter I mentioned. And we're going to call W, this factor here, disorder, the disorder parameter. So at each site, we're going to randomly sample a value between minus W and W. And we're going to localize it at that point. And we're going to do this for many realizations of the data so that you have sort of a large number of these guys that you can average over and talk about. And the way to understand localization is to look at the Hamiltonian. So the first term is essentially just isolated quantum particles. The second term is encoding the interaction between these particles. And so you can imagine that if we separate these particles altogether, so we make J0, that's like cutting off these legs between the vertices. And in that case, we just have basically a purely quantum mechanical system, and we have pure unitary evolution. We can recover all the initial conditions from whatever final state we end up at. So then we take J and we don't let it be zero. We make it a little bit non-zero, but still much smaller than the disorder parameter. What do we see there? Well, in that case, you can still solve exactly for the many-body eigenstates using perturbation theory. So in this case, we still have our sort of a unitarity winning the battle. Where the system gets interesting is where the disorder parameter and the sort of coupling constant between these guys gets become of, well, roughly relatively the same strength. And it's in that regime where you can no longer use your perturbation theory, and you want to ask the question there of who wins between thermalization and unitarity. Right. So this is the sort of, we're keeping the whole picture in mind. We can sort of have an initial part of a question that we can ask, that we want the neural network to try and solve. And that is, can we classify a system as being in either the thermalizing or localizing regime for a given value of disorder? Remember, disorder is this W parameter. Right. So thinking ahead a little bit further, we have a good idea of what we want out, and that's a probability that what the input corresponds to is something that is localizing or thermalizing. We will discuss what the neural network structure will be later, but one thing that we need coming out of the physical problem is the input to the neural network. So currently, the only thing I've told you is that the disorder parameter is what's going to be going to tell us about whether or not the system thermalizes or localizes. But if we imagine what that would look like, the network can only give us basically a single line heat map of whether or not it's thermalizing or localizing. So there's not really much information encoded in that other than some critical disorder value. And yeah, so we would like to figure out a little bit more about the transition between thermalization and localization. And we also, in order to do that, we need to make use of these well-defined, of some sort of idea of well-defined regime. So a well-defined regime here is this small value of J with respect to W. And we know that that's where unitarity wins, so localization wins. Right. So we need to try and figure out, okay, so one of the key issues here was what is the input to the neural network? And what we're going to use is the entanglement spectrum. So what is that? Suppose I have this initial green state. So that's the whole system. And that system is in a state psi. From that state, I can construct a density matrix, which is just ket psi bra psi. And now I partition the system, and so I cut it in some way, and I have a system of interest, which we'll call A, and a system that I am not really interested in, and I want to see if it acts as a reservoir, which we call B. So by performing that partition, I've now separated psi into being an element of the product Hilbert space, so that's subspace A and subspace B. And now I trace over the degrees of freedom of B to get the reduced density matrix for the A subsystem. Now, from that, I get what's called the entanglement Hamiltonian, and it's related to the reduced density matrix via this relation. And so what I'm going to do to get the entanglement spectrum, so the entanglement spectrum are just the eigenvalues of the entanglement Hamiltonian. What I'm going to do to get the entanglement spectrum is I'm going to solve for the eigenvalues of the reduced density matrix, and then I'm going to take the negative log of them, and that's going to give me the entanglement spectrum. Okay, so that's what we're going to give to what the neural network is going to take in as an input is the entanglement spectrum. Naturally, a good question to ask is, why is that a good choice of input? And it's so there's several reasons, and I'll sort of brush over them quite quickly. But the difference between the largest two eigenvalues is called the Schmidt gap. And that's approximately 1 for many-body localization and 0 for, ETH is the eigenstate thermalization hypothesis, but we're going to say that approximately 0 for thermalizing states. For the entanglement entropy, which is just defined as basically this thing that looks a little bit like an entropy, that scales in a way that, scales in proportion to volume for thermalizing states and area for localizing states. The standard deviation of the entanglement entropy is much less than 1 when it's far from it. So when it's definitely localizing or definitely thermalizing, the standard deviation of the entanglement entropy is small. And finally, the entanglement entropy spectrum spacings have known specific distributions in the localizing and thermalizing phase. Right, so we have now isolated the input for the neural network. We've said that we've sort of justified our reasons for choice in that input. And now we need something to benchmark against. And this refers to that sort of much earlier comment about knowing what a well-defined regime is. So work by WITS et al., exact numerical simulations were done. And so this is the normalized shifted eigenvalues. So you take your eigenvalues and you force them to be in a bucket between 0 and 1. And so that here they have this ergodic or thermalizing regime and this localizing regime. And what I want you to sort of remember is the shape of this transition region. I'll show it to you again later, but that's what we're going to want the neural network to reproduce. Okay, and then finally, there's something which I'm sort of very quickly brushing over, which is how we actually get the entanglement spectrum out, how we code the Hamiltonians, and do the numerics for getting the entanglement entropy out, which I'm just going to basically say that there's not enough time to give details for here. And if you want to, these systems require lots of memory and parallelism. So yeah, there's lots we can talk about there. I'm not going to talk about it now, but take it on faith and send me an email if you don't believe me or if you want to discuss it. We have the numerics to discuss, to produce these entanglement spectra for these quantum graph-like Hamiltonians. Okay. So onto the neural network side of things a little bit more precisely. Okay, so we're going to use something called the multi-layer perceptron. I think Professor Schock talked about perceptrons in the first talk. And yeah, so I'll try and give you a brief overview of how we get to a multi-layer perceptron from a single layer perceptron. And so what we're going to end up doing is taking a single layer perceptron, stacking them into multiple single layer perceptrons, and then stacking those into what's called a multi-layer perceptron. Okay, so the input to the neural network. So this is going to be the entanglement spectrum. So here are our input components. This is what we're feeding into the network. The weights are going to be what the network is trying to optimize through the training process. And then it's going to get to some, it's going to get to a node. It's going to sum the product of the weights times the input. And here I've just used the threshold function as the activation function. The activation function is, in this case, is just an on-off button for whether or not the value is 0 or 1. And so in this case, if we just wanted to classify as localizing or thermalizing without any sort of continuity between them, we could do that using a threshold function. So this is the model of a single perceptron, right? So now onto multiple single layer perceptrons. So if you just focus on an individual node here, and you track it back, all you have is the same thing we had in the previous diagram. So that's your input fed through some weights, and something happens here. I haven't specified the activation function here, but in this case, you can sort of see if I label these weights, and by labeling the inputs, you can sort of see that the matrix structure or matrix multiplication comes out. So yeah, and these YIs will, okay, so this is multiple single layer perceptrons. The YIs are going to feed into the next layer of the neural network. And yeah, so one quick thing, a justification for using a multi-layer perceptron comes from this idea of the universal approximation theorems, which very loosely states that a multi-layer perceptron can accurately model any function of the inputs given enough internal parameters. And yeah, that's not exactly right, I apologize. So that's why we're using a multi-layer perceptron. And so what we have here is the sort of general model of the network. What we'll have is the entanglement spectrum as input. It'll go through, be multiplied through by the weights. Here we have a summation of the results, an activation function, which isn't just binary. So this looks a bit like arctan. And then we feed the output of that sort of first stacked layer of single perceptrons as the input to the next layer. And here I've got something called the softmax function as the activation function. And what the softmax function does is it acts as a sort of data normalizer. That probably should be in inverted commas. So what it means is that the output of the network is going to be a probability of being in class I for however many classes you have. We only have 2, thermalizing and localizing, given input X, the weights W, and activation function F, okay? So great, we have the neural network, we now have a way of structuring it so that we can get a probability that the input corresponds to localizing or thermalizing, and yeah, cool. Okay, so what I've told you about is essentially what's at the bottom here. This is the extracted network, but during training, well, training is slightly more complicated, and I'm going to I'm going to have to leave out a bunch of stuff when talking about this, but hopefully you get an idea of what's being done during training. So when comparing these two, you can sort of see how you can extract this bottom network from the top one. And I've sort of done that for you all here, but there's still a bunch of things which aren't accounted for. So I've got something called a drop layer here. I've got this region here. Something that looks unsupervised and something that looks supervised. And sort of what do these things all do during training? And so what we're going to do is we're going to study these points. Well, I'm going to try and explain these points of interest so that yeah, well, we know why they're there and why we remove them in future. So during training, we're going to implement, okay, so first we're going to talk about the drop layer. So this is actually something that's performing dropout regularization. So what that does is during each training cycle, it's going to just turn off the weights associated to one of the inputs so that that doesn't affect any of the outputs. And what that does, it reduces codependencies within the network. So it's just randomly selecting them in each run. Randomly selecting nodes to be excluded. And when we did training, I think we chose it to select around I think half of the neurons in each run. So in each run, it would just completely remove the connections to half of them. And that was, to prevent overfitting and codependencies in the network. Right. So now referring back to this, we're going to talk a bit about the supervised learning part of the network. So for supervised learning, you have an input and an expected output. And that expected output you call a target. And so that's basically like saying, I know what state this is in, and I'm telling you what you should get, what you should be getting out of this. And that, I mean, if you look at this diagram here, there's a region here where you feel very confident you can say that things are thermalizing, and a region here where you're very confident you can say things are localizing. So that's exactly how we choose the training data. So what we're going to do is we're going to produce data at a given value of disorder, and we're going to say if that data is produced for disorder of 0.25, we're going to call it thermalizing, and we're going to give it a target of 10. If it's produced for a disorder of 12, we're going to call it localizing and give it a target of 0.1. And what you're going to do during supervised learning is penalize the neural network for how far away it is from being correct. And how you do that is by making use of the cross-entropy cost function. Okay. Now, what that does is, okay, so if you can imagine your output being potentially 3-dimensional or n-dimensional, you won't necessarily have a 0, 1, you might have 0, 0.5, 0.5. And what you're going to do is you're going to sum over them. In our case, the only thing that's going to contribute is when you have a 1 in the target. And so for that 1, it's going to measure, okay, so two things to note is that this thing, this cost function is 0 when ZK is 1. So if you're hitting that target perfectly, you get something that's 0, or you're moving towards it. And that's, well, we use the negative sign to basically make it a positive function. And so we're going to get, during training, the network is going to be trying to minimize this cross-entropy cost function. Right, so that's the supervised learning. Now onto the unsupervised learning. So the unsupervised learning is not actually completely necessary, but the reason why we're going to implement it is because we're actually interested in this transition region between the definitely localizing and definitely thermalizing states. So it's this in-between region where we really want the network to be confident and to make precise statements. And so because we're training on these extremal values, the network is susceptible to being, to indecision in this intermediate regime. And so we want to penalize the network for any agnosticism. We want it to be very confident in the classifications it's making, especially in the intermediate region. And how we're going to do that is that for each supervised input, okay, so that's the supervised learning with a target, we're going to generate a different input with disorder that's somewhere in the intermediate region. And that's going to be randomly sampled, so you get a pretty good distribution of disorders. And these come with no target value. So we're going to ask the network to churn out a value based on these intermediate disorders. And then we're going to add an additional cost function, the negative Shannon entropy. And again, so previously for the supervised learning, we had the target and the output of the network. In this case, we just have the output of the network as being involved in the cost function. And again, here it'll be minimized for being precise. So if you're close to 0 or close to 1, this function is minimal. And obviously 0 at 1 or 0. Okay. So now we can see, the full structure of the neural network, or sorry, the training network. We see that there's an unsupervised input, and that's going to go through the contribute to a confidence penalty. The supervised input, that's going to contribute to the cross entropy cost function, the dropout regularization, and there's something which I haven't spoken about, but there isn't quite time to, called weight decay. And we're gonna add a cost function for weight decay. So what weight decay is it says that if we look at one of these these networks, so if weights contribute to the accuracy of the network in a given training run, that's good. But if they don't contribute to the accuracy of the network further, they should decay to 0. And so you use weight decay to basically make the weights decay to 0 if they're no longer contributing to the accuracy of the network. And so how that's implemented is by including this L2 regularization term for the norm of the weights. And so our cost function that we're going to try and minimize for the network is, so here's our supervised term, the cross entropy cost function, gamma times the confidence penalty, and beta times the L2 regularization. So I've added these hyperparameters gamma and beta because we don't know how important each of these costs or these contributions to the cost function are going to be. And so we're going to try and figure out if we can optimize them in some way and to get the best possible results out of the network. Okay, and this is just a note. In talking about the network, there are a whole bunch of things I just had to completely neglect because there just isn't time to talk about them all. So I sort of loosely introduced weight decay in that last slide. I haven't spoken about how to choose activation functions. I haven't spoken about backpropagation or how the network is updated during training. I haven't spoken about how you choose a gradient descent method. I haven't spoken about mini batches, which is a way of batching your training samples. I haven't spoken about how to initialize the weights of the network because you can't start them with all zeros. I mean, you can, but that would be a poor choice. And probably some other things too. Right, so this is, again, I put it back in the slides to re-emphasize it. So this is the numerical benchmark we want to achieve. Here, oh, whoopsie. Here, the lowercase h is their disorder parameter, and we're going to want to, for us, our disorder parameter is W. And so we're making use of the well-known regimes here where it's thermalizing and localizing for training, and we're going to want the neural network to fill in the gaps for the systems as you increase disorder through that intermediate region. Okay, but first let's have a look at how the confidence penalty and weight decay actually contribute to the accuracy of the network. Okay, so this is the key image that we want to reproduce. So first, weight decay. This is the beta hyperparameter. So the black squares here represent the Lloyd et al. Data. So they are sampled from, I think the entanglement entropy, so the green dots in this image. And so you can see without weight decay, the transition region is sort of pushed far to, the disorder region for transition is far too great for what we would actually like. And when we add that weight decay, it pushes that transition region back to lower disorders. Okay. And now the effects of confidence optimization. And I would not blame anyone for looking at this image and thinking that there is no real benefit from confidence optimization. It certainly doesn't seem obvious to me when looking at these two images that the second image is a better approximation of the black dots than the first one. So yeah. Oh, and I suppose one thing I should say is that, so the heat map here is 1 for localizing and 0 for thermalizing. So as you move from, it's moving from thermalizing to localizing. So promising effects from weight decay, not looking so good from confidence optimization. What about if we consider them at the same time? Well, this is where confidence optimization finally gets to shine a bit. So starting in the top left, this is just with both of them turned off. As we move to the right, we're increasing our weight decay. And as we move down, we're increasing our confidence penalty. And as you can see, so this is just the original. So these two images, top left and top right, correspond to the effects of weight decay, the ones that we saw there. As we move down, you can see that the network, so this yellowy region is region of a bit of uncertainty. And that region is compressed right down to something that looks very, very similar to the target data by including the confidence penalty. And so with the confidence penalty and with weight decay, we're quite confident that the neural network has learned how to classify the entanglement spectrum as being localizing or thermalizing. So this is great. Another representation of this data is to sort of invert the images so that it's cold or zero where the network is confident and hot where the network is uncertain. And when you do that, you can also see the effects of the confidence penalty and weight decay. So again, moving left to right is increasing your weight decay, and top to bottom is increasing your confidence penalty. So we see the pushing back of the transition region by weight decay, and we see the reduction in the uncertainty and the width of that uncertainty region using confidence optimization. Okay, so we're quite confident the network is doing something, well, has learned something about many-body localization and the classification of entanglement spectra. And now we can ask questions like, is our network predicting anything different about system sizes or where the transition region is? And the answer is no. Both of these model the data very well. And the difference, or a key difference, seems to be that when you increase the system size, you are reducing the width of that uncertainty region. Okay, so here we're making use of the same variable, that normalized shifted eigenstate variable, so putting everything between 0 and 1. But an alternative way to do this is to literally label, order the eigenvalues from 1 to n, and to bin them into groups of, in this case, for n equals 16, 128 eigenvalues, and for n equals 12, or 8 eigenvalues. And the reason why we do that is because you'll recall earlier I said we're interested in how the network classifies different topologies. And so when you're producing these images, you're still performing some sort of energy binning. And you can be, if you understand the system well, you know how to choose the widths of those energy bins. When you don't know what those energy bins are, or what an appropriate choice for those bins are, you can't actually guarantee that you're going to have anything in a given bin. And if you need to normalize the data by something that's in the bin, you'll get a division by 0 or something like that. And so your long, hard, your run on the high performance computer is going to return an error, and you'll have wasted years or weeks or months of computation time, not of actual time. So this is just a slightly different representation. So you can see that in the normalized shifted eigenvalue one, it's like sort of got a slight bulge for lower eigenvalues, and that's slightly masked when you use the binned eigenvalue number representation. But these are just representations of exactly the same data, just binned in different ways. Okay, but this one, the alternative, the eigenvalue number bins, is slightly more reliable because there you don't have to count on anything being any eigenenergy being in a specific bin. You are guaranteed because you're just labeling the bins and grouping them according to 128 or 8. Okay, right. So this is the key thing we want to check now. So we are now confident that the network is reproducing accurate results for this nearest neighbor model, so this ring model spin system. And now we're going to want to check whether or not this learning that the network has done is transferable. So we want to see if the network can demonstrate transfer learning. And to test that, we're going to give it these systems that are similar, but still quite distinct topologically. So the most similar system, again, is this Majumdar-Ghosh model, which is nearest neighbor and next to nearest neighbor connections. The other models are quite distinct in that they have a central spin, which is connected to all the others. So here we have a central spin connected to all the others, but still have nearest neighbor connections. Here we have just one central spin that's connected to all the others. And yeah, so we're confident in this problem. What does the neural network predict about these different topologies? Okay, so first, well, roughly the same statement I made just on the slide. So first, we're going to study the wheel model. So we're looking at so we've studied this, we're now looking at this model. So what does the neural network predict for this model? Well, so previously we had in our presentation of the results, the disorder value running from 0 to 4. In this case, the disorder values are running from 0 to 10 in order to see the transition region. And so the prediction here is that the transition region is pushed out towards sort of just above 4, around 5. But anyway, the key takeaway is that the central transition region has been pushed out significantly. So that's the prediction of the network. Again, the statement that I've made here is just a little warning that this uses the binned eigenvalue number, the binned eigenvalue representation, binned eigenvalue number representation, as opposed to the epsilon representation. And so when you run the numerics, what do you find? Well, for the wheel model, it predicts almost the same thing. So the black dots are the Neupert data, sorry, not the Neupert data, the WITS et al. Data, the data we wanted to model, or the data for that original ring. And what do we see? Well, that transition region has been pushed out significantly. And here the central region is around 5. So that's great. The network seems to be making reasonable predictions. I'm not going to make any definite statements about numerically accurate, but reasonable predictions about what you should see when you have this wheel model. Okay, so now let's have a look at the star model. So, right, what's predicted for the star model? So here we see these peculiar regions of uncertainty at low disorder. And we're not really, we associate that to lots of degeneracy in the star model, in the eigenvalues of the star model. And we also see that, again, there's this push out of the transition region. Previously, it was at about 5. So here it's not quite at 5, it's closer to 4. And again, the same warning for the data representation. So when you run the numerics, what do these predictions come to be found as accurate? Well, yes, and quite astonishingly, that weird region of uncertainty is also picked up by that you see in the numerics, and it's found by the neural network. But remember, the neural network has not been trained on any of this data. It's been classifying a completely different system. So it's an impressive feat that it does this. It also, again, you see this push out of the transition region to around, okay, in this case, 4. So that's fantastic, or just above 4. So excellent. So numerically, it looks okay. Qualitatively, making very good, reasonable predictions on stuff it's never seen before. So finally, let's talk about this Majumdar-Ghosh model. Now, this model is the one that's most similar to the model we started with. The only difference is we've got additional connections to the next nearest neighbors. So what does the network predict about the Majumdar-Ghosh model? Well, in this case, the transition region is around, so previously it was around 1.5 for the nearest neighbors only. For this Majumdar-Ghosh model, it's sort of pushed out towards 3. And so what do the numerics tell us? Well, the numerics tell us approximately the same thing, that if you study this model and you put it through, and then you ask where the transition region is, it's pushed out to around 3. So that transition region that originally was around 1.5 is now at about 3. And so this is not I wouldn't quite call it miraculous, but a very, very interesting result because the neural network appears to have learned something fundamental about localization that is not unique to the ring topology we started with. And so when we sort of collect the predictions of the network and we look at the structure here, it looks like as you increase sort of connectivity or the shortest path length, you push out your disorder region. So this would be the longest path length, second longest path length, second shortest path length, and shortest path length. So as we increase the connectivity or shortest path length, we are heading towards pushing out this transition region. And that prediction is something that comes courtesy of not just the numerics, but a prediction from the neural network itself. And when you look at these things side by side, unfortunately, the ranges on these plots are different. So this is 0 to 4, 0 to 6, 0 to 10, and 0 to 10 for the top and the bottom data. But you can see that the neural network seems to have learned something fundamental about these localizing states, or this transition region in particular. And so really the point I want to leave you with after this sort of lecture talk thing is that neural networks you might also be useful as an experimental tool for probing systems where you don't necessarily know what you might get. And I'm not going to make statements about numerical accuracy of the predictions of the network, but what can be said is that it's certainly worth, given the network's predictions and their agreement with the numerics, it's tempting to explore problems that have not been studied and to gain an intuition for them using a neural network, sort of like experimenting in the dark a bit, and then trying to either analytically solve where possible or numerically solve where possible to corroborate the results. And so neural networks might be a useful tool for exploring unknown regimes of various systems. And yeah, that's all I really wanted to say. So thank you for listening, and thank you to the NRF for funding this research, and to the UCT high performance computing team for letting me use their systems. So yeah, thanks guys.